Good afternoon. Let us arrive at the principal strain and their directions. In the previous videos, we have talked about principal stress. So similarly, we will have principal strain. So the planes on which there is no shear strain, that is only normal strain, that is epsilon x, epsilon y, epsilon z exist. Those planes are called as principal planes, and the corresponding strain in those directions of the principal planes are known as principal strain. Okay, the two mutually perpendicular principal strain directions are always such that the corresponding shear strain is 0. So gamma theta is 0. So in the previous slide we have seen gamma theta formula is epsilon x minus epsilon y minus epsilon z times sine 2 theta plus gamma xy cos 2 theta is equal to 0. Yes, so epsilon 1 and 2, you can calculate it as epsilon x plus epsilon y by 2 plus or minus half under root of epsilon x minus epsilon y the whole square plus gamma square xy. And how are we going to find the angle? Tan 2 theta is gamma xy times epsilon y minus epsilon x. So the two values of theta, they differ by 90 degrees. Hence, theta 1 is say alpha, theta 2 is going to be alpha plus pi by 2. Alright. So next is strain invariance. You need the value or formula of epsilon 1 to tan theta to solve the problems regarding principal strain and its directions. So next is strain invariance. So epsilon x minus epsilon yx, epsilon zx, then epsilon xy, epsilon y minus epsilon zy, epsilon xz, epsilon yz, epsilon z minus epsilon. That if we consider this to be in the form of a determinant and equal to 0, if you expand this determinant, you will be getting the values of strain invariant. So this gets reduced to epsilon cube minus j1 times epsilon square plus j2 epsilon minus j3 equals 0. So j1 is nothing but epsilon x plus epsilon y plus epsilon z, and the value of j2 is epsilon x epsilon y plus epsilon y epsilon z plus epsilon z epsilon x minus 1 by 4 times gamma square xy plus gamma square yz plus gamma square zx. Alright, then j3 is equal to gamma x, gamma y, gamma z plus 1 by 4 times, sorry, j3 is epsilon x, epsilon y, epsilon z plus 1 by 4 times gamma xy, gamma yz, gamma zx minus epsilon x, gamma square yz minus epsilon y, gamma square zx minus epsilon z, gamma square xy. This is completely as per how we have found out stress invariance. Similarly, I am finding out strain invariance. So only the epsilon and gamma will be replaced in those formulas. So next is strain transformation. Strain transformation. Alright, So if the displacement components are going to be u, v and w at a point in terms of functions say x, y and z respectively with respect to the Cartesian coordinate system, then if at the same point the strain components are going to be u dash, v dash, w dash with reference to another set of coordinate axes, that is x dash, y dash, z dash respectively, then it is epsilon x dash gamma y dash x dash by 2 gamma z dash x dash by 2 and then gamma x dash y dash by 2 epsilon y dash gamma z dash y dash by 2 gamma x dash z dash by 2 gamma y dash z dash by 2 epsilon z dash. This is equal to the direction cosines L1, L2, L3, M1, M2, M3, N1, N2, N3, then another matrix epsilon x gamma yx by 2 gamma zx by 2 gamma xy by 2 epsilon y gamma zy by 2 gamma xz by 2 gamma yz by 2 epsilon z times the transpose of your direction cosines L1, M1, N1, L2, M2, N2, this is N, then L3, M3, N3, or I can just write it as epsilon dash is equal to A times epsilon into A transpose. What is A matrix? Direction cosines. Next, spherical and deviatorial strain. Okay, so strain tensor can be divided into two parts, that is spherical strain and then deviatorial strain. So I can write strain as spherical and deviatorial, where this is E double dash is spherical strain. There's nothing but this particular matrix, and then E dash is deviatorial strain, and that is epsilon x minus epsilon m, epsilon yx, epsilon zx, epsilon xy, epsilon y minus epsilon m, epsilon xy, epsilon xz, epsilon yz, epsilon z minus epsilon m. So this is deviatorial. Mean stress, epsilon m is nothing but mean strain. It is mean strain given by epsilon x plus epsilon y by epsilon z divided by 3. Alright, this is epsilon z, epsilon z. So whatever topics we have covered in this video, everything has its counterpart with respect to stress. That is stress transformation, stress, spherical and deviatorial stresses, then principal stress and their direction. So I've just taken the same thing and then converted with respect to the strain. I've written all the values with respect to the strain. We are going to have problems with respect to this.